Hello everyone. Welcome to the live interactive session on geology and soil mechanics. All of us are meeting after a long gap between. So there were some issues, which due to which we had to postpone and prepone some sessions. So today's session is basically the seventh week session, and on Friday again we will be having a discussion session from 6 to 8 p.m. That will be on the eighth week lectures. Okay, so today it will be on the seventh week lectures, and on Friday it will be on the eighth week lectures. So till today we have studied many things, starting from the basic sorry, index properties. Oh, excuse me, please. Starting from the basic index properties, then we studied the in situ stresses, then we saw what is seepage, how to solve seepage problems, and all those things. So today we'll be continuing our discussion with the consolidation topic. All right, so today we'll be continuing a discussion on the topic of consolidation. We'll be solving some problems, and yeah, that's all. So let us start. So this E versus right, so this void ratio versus pressure plots, this already we have seen in the previous sessions, right? So this we've already seen in the previous session. So when we do a consolidation test, one-dimensional consolidation test, from that one-dimensional consolidation test, we can get this E versus pressure plots. Okay, void ratio versus pressure plots. And so you see, if as with increase in effective pressure, with increase in effective pressure, with increase in effective pressure, the void ratio actually reduces. Okay, with increasing effective pressure, the void ratio reduces. Now, if you want to extend this E versus pressure plot, we can see this where in this pressure plot, E versus pressure plot, we have the loading part, then unloading part, and the reloading part. So all these parts curves are shown here: the loading, unloading, and then the reloading. The reloading curve has a flatter slope. So this was the original loading part. So this has a steeper slope, and this is the reloading part. So this part you can see has a flatter slope. Now, what is the pre-consolidation pressure? The pre-consolidation pressure is the maximum effective pass pressure. So say you have loaded up to this point, right? And then you have started reloading. Okay, reloading and unloading. Say you have started reloading. So for a soil which is at this state, this is the maximum pass pressure. This is the maximum pass pressure that it has undergone. So the pre-consolidation pressure will be nothing but this. All right. Now, how can we actually determine this pre-consolidation pressure graphically? Okay, so say you get the E versus P plot, pressure plots uh, for a soil from the site by doing the one-dimensional consolidation test, and then you want to know the pre-consolidation pressure. So how do we actually to find out the pre-consolidation pressure? We can do this graphically. Okay, so Casagrande in 1936 gave this graphical method using which we can get the pre-consolidation pressure graphically. Okay, so how to do that? So you can see first we have our curve, right? So we have our curve. Now, just by looking at the curve, we draw a straight line. Okay, we draw a straight line AB at the point A, just by your visual judgment, the point where the curve has the maximum radius of curvature. At the point where the curve has the maximum radius of curvature, we have to just judge this by our uh, visual judgment. Okay, we have to have a visual judgment and then mark the point A, which has the maximum radius of curvature. Now at the point A, we have to draw a straight line AB. Okay, draw a straight line AB. Now, again at the point A, what you will do? we will draw a tangent AC at that point A, tangent to the curve AC at that point. So now we have two lines AB and AC, right? AB and AC, and we have this angle CAB, which is formed at the point A. After that, what we do, we bisect this angle. Okay, we draw the angle bisector. We draw this angle bisector here for this angle CAB. Alright. Now what we do? Now you can see we have this straight part, straight lagging part of this curve, right? So we extend this part to intersect the angle bisector AB at the angle bisector AD. Okay, angle bisector AD at the point F. Okay, at the point F. Now, as we get this point F, the axis or the x coordinate of this point X is nothing but our point F is nothing but our pre-consolidation pressure. So the x coordinate of our point F is nothing but the pre-consolidation pressure. So this is how we need to find out the pre-consolidation pressure graphically. So first what you do from the void ratio versus pressure plot by visual judgment. By visual judgment, we draw a straight line at the point where the radius of curvature of the curve is the maximum. Then we draw a tangent at that point. Again, we draw a tangent at that point, and after that we bisect the angle and draw the angle bisector. Post that, what we do, we extend the straight lagging edge of the curve to meet the point AD, and from that point, the x-axis of that point will be giving us the pre-consolidation pressure. Okay. Okay. Yeah. Now, see, so we have this curve, right? So we have our void ratio, we have our pressure. Okay. Now say we have some curve like this, and then here we have the pre-consolidation stress. Now, if if the initial stress of the soil is here, sigma naught, and then after increasing the soil, see, the first case is sigma naught plus delta sigma, that is the sigma dot is the initial stress, the increase in stress, that increase in stress is delta sigma. Now, after increasing stress also, the stress is less than this delta, this sigma c, this is a pre-consolidation stress, that means here itself. Okay. Okay, so this much is our delta sigma. This is the first case. So in that case, what we do, if you want to find out the settlement, we use this relation. CSH 1 plus C naught log sigma naught plus delta sigma by sigma naught. So now what is CS? CS is nothing but the slope of our rebound curve. Okay, rebound curve. Okay, slope of the rebound curve. Now, if say our delta sigma naught is this much, delta sigma is this much. For delta sigma is this much, then first for this up to this level we have to use the CS, and for here to here we will use the CC. This is the coefficient of what CC, coefficient of consolidation, I think, right? Which we had studied in the previous class, CC. So you see for the first for the stress from here to here we use CS, and then for the stress from here to here we use the CC. Okay. And finally, when both the sigma naught and sigma naught is actually after this part, the initial stress is greater than the pre-consolidation stress. And obviously, what we do, use the CC itself. Okay. Now next is the secondary consolidation. This was our how to calculate the primary settlement, primary consolidation. Okay, primary consolidation. Now, how do we calculate the secondary consolidation settlement? Now, what do you mean by secondary consolidation settlement? Secondary consolidation settlement is what that happens due to the plastic readjustment of the soil post the primary consolidation. So that is our secondary consolidation. This is nothing but kind of creep in the soil. So as time passes, how the consolidation of the soil happens, that is nothing but a secondary consolidation. So for that, how we do? Same settlement equal to C alpha dot H log T2 by T1, and you can see what T2 and T1 here from here, right? So this is how we calculate. Okay, so what is C alpha? C alpha prime? C alpha prime is related to C alpha with this relation. Okay, then what is EP? EP is the word ratio of the end of primary consolidation and all those things. And what is C alpha? You can see what C alpha. Okay, so everything is depicted here clearly. You can easily calculate the secondary consolidation settlement using this procedure. Now, what is Terzagi's one-dimensional consolidation theory? Okay, so I am not going to go through the entire derivation of it. So this has already been discussed in the main theory classes, I suppose. So we are not going to repeat it again now. So this Terzagi's one-dimensional consolidation theory is one of the most important theories in our soil mechanics. Okay, so this actually defines the consolidation procedure. Okay, consolidation procedure and helps us to calculate how much time it it requires for a soil to undergo a certain amount of consolidation settlement. Okay, so this Terzaghi's one-dimensional consolidation theory helps us to calculate the time required for a soil to achieve a certain degree of consolidation. Okay, achieve a certain degree of consolidation, how much time is required. So you can see you have a second order partial differential equation that is that defines the Terzaghi's one-dimensional consolidation theory. It is dou u by dou t equal to Cv dou square v by dou t square. Now Cv is nothing but the coefficient of consolidation. Cv is nothing but the coefficient of consolidation, and the coefficient of consolidation is related to the coefficient of permeability and the coefficient of volume compressibility as well as the unit weight of water. Because Cv is equal to k by gamma w into mb. Okay, k by gamma w into mb. So this is our Cv. All right. So now you can see this clay layer here. This clay layer here is the consolidating layer. Okay, this layer is going to consolidate and settle. All right, and this sand is nothing but a drainage layer. So the water that is there in the clay, it is going to drain out both in the top and bottom. It is a double drainage condition. The thickness of the clay layer is considered as 2h into dr. It is the total thickness of the clay layer. What are the boundary conditions? At z equal to 0, the pore water pressure is going to be 0, right here, because immediately the water is going to drain out, so the pore water pressure is going to be 0. Now it is z equal to 2 hdr, that is here at this level. Again, the pore water pressure is going to be 0. Excess pore water pressure is going to be 0 because immediately the water is going to drain out from there, right? Also, at time t equal to 0, the initial pore water pressure across the soil layer is assumed as U is equal to U naught. Now, for this partial differential equation, then we can get the solution by separation of variables and other techniques as this. So, this is the solution of this partial differential equation that we can derive. I'm not going into the exact like procedure of solution. You can find it in the textbooks or in the main lectures. Okay, the textbooks, there are soil mechanics textbooks where you can find this. So this is the solution that we get. Now in this solution, you can see one value, that is TV. TV is nothing but a time factor that we'll see in the next. What is the time factor? Now TV is the time factor. So what is TV? TV is equal to CVT by HDR square. Now CV is nothing but a coefficient of consolidation. Coefficient of consolidation, and T is the time. Okay, T is the time, and HDR is nothing but the drainage path. So square of the drainage path. Now if we see here, twice HDR is the total just a second. Yeah. So 2 HDR is the total thickness of the clay layer. For the drainage path, as we have double drainage, the drainage is happening on both the directions. So our drainage path will be this much. So HDR. So to square of the drainage path, square of the distance of the drainage path, axial drainage path. Now, at any depth set, so you have any, so at different depths of the clay layer, you will having a different degree of consolidation. Now, how to get that? The degree of consolidation at any depth z at any time t uz is nothing but 1 minus uz by u naught. Now, what is small uz? Small uz is the excess pore water pressure at any time t, and u naught is the initial excess pore water pressure. Okay. Now, say we have a clay layer. Now, at any depth z, initially before the consolidation pressure, consolidation started, the uh, pore water pressure was u naught. Now, as soon as we apply the load, excess pore water pressure is going to develop, and then it's going to dissipate. It's going to start dissipation. So at any time t, the excess pore water pressure is uz. Just a second, na? Let's give this. Yeah. So at time t, the pore water pressure is going to dissipate, and then it's going to reach to uz. Okay, from that we can get the degree of consolidation. Okay, degree of consolidation at that point. This is a capital uz or capital U. Now we can see for degree of consolidation 0 to 60%, the time factor and the degree of consolidation are related. So TV is equal to pi by 4 U by 100. And for degree of consolidation greater than 60%, TV is nothing but 1.781 minus 0.933 log 100 minus U. So you solve some problems using this. That time it will get more clear how we can use this. Okay. Now, if you see this graph, you can see you have Z by HDR in one side, and you have the degree of consolidation in the other side. Okay. Now, yeah, right. So at the center, you can see. So the time factors are marked here. Okay, the time factors actually relate the time. Okay, the time. So now you can see at zero time means here. Zero time means here. Zero time here. The degree of consolidation is 0. Now, as you increase the time factor will also increase. So, say we have a time factor of 0.1. A time factor of 0.1 at the center, at the middle of the layer, we have the least degree of consolidation. Okay, least degree of consolidation. Now, and at these edges, at the boundary of the layer, that is here, you have the 100% consolidation. This is degree of consolidation 1. Obviously, because at the edges directly the water is draining out, so degree of consolidation will be 1. Okay, and at intermediate points we have different degrees of consolidation. Again, we increase the time, so we have time factor also increases. We have a different graph. So this way we can plot this. Okay, from the solution, from this solution we can plot this. Okay, now what let us do? Let us just solve some of the problems. Then everything will be more clear. Okay. Yeah. let's start solving them. Just give me 1 second now. Yeah. So let us solve the problems now. Yeah. So for the soil profile shown in the figure, initially water table is 5 meters below the ground level, which is lowered permanently to a depth of 15 meter below ground level by pumping over few years. Assuming unit weight of water as 10 kilonewtons per meter cube, unit weight of sand above water table is 18 kilonewtons per meter cube, and unit weight of sand and clay below the water table equals to 20 kilonewtons per meter. And the coefficient of volume compressibility, this MV, is 0.25 meter cube per meganewton. Determine the settlement of clay in millimeters due to lowering of the water table. Okay, so initially there is a high level of water table, and then the layer of water table reduces. So what will happen if water table gets lower? The effective stress is going to increase in the soil, and if effective stress increases, then what is going to happen? Consolidation is going to take place. We need to find out this the settlement. Okay, this settlement. So now let us first find out the initial initial stress, effective stress here before at this level before the lowering of the water table. Okay. So 5, this is 5 times uh what is the just a second. Unit weight of sand above water table it is 18. So 5 into 18 plus 15. So then we have from here to here. So it's 20 20 minus 5. 20 minus. Just a second. So this is sand. This is clay, right? So 15. Just a second. 5 into 18 plus. Directly we can do. Water table is here, right? So it's 5 into 18, and then we have this much from here to here. Here to is 20 minus 5. 20 minus 5 times how much? Minus what is the unit weight of sand and clay below water table is 20. The submerge is minus 10. This is the unit weight of water. So this is nothing but gamma W. Okay, plus this much. This much is done. Sorry, this much. 2.5 times 20 minus 10. Okay, understood. So 5 into 18, then we have 15 into 10, and then we have this 2.5 into 10. Okay, okay. So 5 into 18, then to here 15 into 10, and then this much 2.5 into 10. Okay, so this will come out as 265. Next, after the water table recedes, let us find out the effective stress. So we have 15 into 18, this much, 15 into 18 plus 5 into how much? 10 plus 2.5 into 10. So this one will come out as 345. You can see with the as the water table reduces, the effective stress increases. This increase in effective stress will start the consolidation settlement in the soil. Okay. So what is the increase in the effective stress? It's 345 minus 265 or 80 kilonewton per square. Okay. Therefore, settlement we have our what we have the coefficient of volume permissibility, right? So you can write this MV, right? So H naught is nothing but the thickness of the clay layer, nothing but 5 times 0.25 MV, 0.5 mega meter cube per meganewton. So meter cube per newton, I will make it 3 times 80. This will come out as 100 mm. Okay, so this much settlement the soil undergoes due to the clay layer. This much settlement the clay layer undergoes due to the recession of the water table. Okay, I hope this problem is clear. It's very simple. Okay, it's very simple. Just we need to calculate the stresses first and find out the increase in stress and directly use the relation which is the settlement to the coefficient of volume polarity. Okay. Now let us see the next problem. So find the settlement in both the layers. Okay, so here we have two layers of soil, AA and BB. These are the two clay layers, and both are undergoing double drainage. You need to find out the settlement of the clay. Everything is given. CC is given. Water content, G, everything is given. From there. You can find out the unit weights, right? So try to calculate this. Okay. First, find out the effective stresses. First, find out the unit weights of the clay layers. Okay, with the given values, find out the unit weight of the clay layer, then calculate the effective stresses. Okay, just try to do it. I will give you 2 minutes. Just try to start the problem, and I will solve it. Try to do it. Try to start the problem. Very simple. Just as I said, first calculate the unit weights first. Unit weight of the clay layer. First, you calculate the unit of the clay. After that, you calculate the effective stresses in at the center of the clay layers. Okay. Layer 1. Into G. So W into G. Saturation is 1. Because C is equal to WG. Saturation is 1. So E is equal to what? WG. So therefore, the effective stress at the center of this 6 times water table is here at the top. Right, after the settlement of the first layer, and 50. Okay, so this will come out as okay. Now next for the layer 2 is layer A, now layer B, same. Okay, same procedure. Okay. Right, understood, right? So 6 into for same 6, then we have 3 into the first clay layer, then we have the 12-meter sand layer, so 12 into 2 29.8 21 9.81 plus 1.5 times this bottom clay layer, right? Okay, so 2 1 is similarly. This one will come out as 11.4. Therefore, total settlement okay. So very simple, right? Just you have to calculate. The main thing is that you have to calculate the effective stresses. That's all. Okay, that's the most tricky part. You can say. That's all. Nothing else. Not at all tricky, right? So easily you can calculate. Okay. Now let us see the next problem. An odometer test is performed on a normally consolidated clay stratum that is 350 centimeters thick. It is 350 centimeters thick. Just a second. Yeah. And it is found that the clay's initial void ratio was 0.8 and its primary compression index is 0.28. The in situ stress at mid-clay layer is 120 and the secondary compression index is 0.02. The building exerts a pressure through its mat foundation of 80 kilonewton per meter square. The time of completion of the primary settlement is approximately 18 months. What is the total consolidation of the 350 centimeter clay strata 5 years after the primary consolidation? Okay. So, yeah. After 5 years of the primary consolidation, we have to find out what will be the consolidation. Okay, let us see. So, try to think about the problem for a bit. Okay. Try to understand what is asked in the question. So both primary and secondary indexes are given. The primary consolidation takes 18 months, and then we need to find out the total after 5 years, the primary consolidation, how much more consolidation takes place. That we are asked. Okay, that we are asked to find out. So try to think about it. How can we approach the problem? What will be the first step? What will be the first step of this problem? First, what we need to do? First, we will calculate the uh, settlement, the values of the settlement. Okay, first we will calculate the values of the settlement. Okay, so let us do that first. Okay, first let us calculate the values of the settlement. Huh? Fine. Huh? So let us do. Okay. So CCH naught 1 plus V naught log 10. Okay. Now what is CC? 0.28 compression index, right? Then we have 350 350 centimeter is the thickness divided by 28 initial void ratio 120 plus 80 120 plus 80 by 120, and this will come out as 12.08 centimeters. Okay, this is the initial primary consolidation. Now how to get the secondary consolidation? Now secondary consolidation we can have 800 E100 means 800 is the thickness at 100% consolidation. E100 is the void ratio at 100% primary consolidation. And T100 is the time required for 100% primary consolidation. Now E100 is equal to naught minus delta E. Now, E100 is equal to E naught minus EC log then have 0.8 minus 0.28. Now 800. So initially was 350. Primary consolidation 12.08 centimeter. So at the end of primary consolidation, the thickness of the layer is this much. Okay. Now you can calculate the secondary settlement. Because the secondary settlement is very less compared to the primary consolidation settlement. This is the total settlement. So initial settlement, okay, initial settlement plus the initial primary consolidation settlement plus the secondary consolidation settlement. Because had a secondary consolidation settlement. Okay, this is comes out total settlement. Okay. Let's see this. How many days would be required by a clay stratum 6 meter thick, draining at both end with an average value of the coefficient of consolidation as this much to attain 50% of its ultimate settlement? Okay. How many days would be required by a clay stratum 6 meter thick, draining at both end with an average value of coefficient of consolidation is CV is this much to attain 50% of its ultimate double drainage condition, 6 meter thick clay layer, average value of coefficient of consolidation is given. So how much time will it need to attain 50% of its ultimate means final settlement, 100% settlement? So that we need to find it. So our CV is so this much is our CV. Okay, this is the CV. Now you have time factor for 0 to 60%. If the degree of consolidation sorry the degree of consolidation is between 0 to 60% and the time factor TV is nothing but pi by 4 u by 100 square. Now for 50% settlement, what is the time factor? Nothing but 0.197. Okay, this is the value of the time factor for 50%. So these values you can remember. Okay, for 50% is 0.197, for 90% if I remember, so it's 0.848 or 83 or something like that. So you can check. So this TV value will need 50% settlement, 90% settlement. What are the TV values? The time factor values. This you should remember for fast calculation. Okay. So T50 I got. This is my T50. Okay. Then uh, then what we need to do? Yeah. We we got T50, right? So after T50, we have this relation CV T50 by okay. So T50, this T50 I know, CV I know. This is the drainage path. Okay, and this is the time required for 50% settlement. All right, now we can have 0.197 CV50 into 10 to the power minus 4 times T50 by D square. Now what is D? D is my drainage path. So drainage path is what? See, 6 meter thick drainage I put that. So it will be 3 squared. Okay, 6 by 2 square. So from here I can get T50 as. So please calculate this. Check how much T50 you are getting. So put the units. So this one I have put in centimeter, but you can see the CV is in centimeters, so it will be 300. Okay, 300 square. Take care of the units, huh? Take care of the units. So this one will come out as 570 days. So for 50% settlement of that ultimate total settlement, 570 days are required. So you can see it's a lot of time, right? Almost 2 years time is required for 50% settlement. And this time is directly related to my coefficient of settlement, coefficient of consolidation. If the coefficient of consolidation is higher, then the time required will be lower. Okay. Okay, so CV is okay, so CV is higher, then the time required will be lower. Okay, if CV is small, then the time required will also be small. And the CV is also directly related to the coefficient of permeability. So obviously, if the soil is more pervious means easily the liquid can flow through the soil, then the time required will be lesser. Okay, and if the soil is less pervious, then the time required for the settlement will be higher. Okay, so this is how everything is related to each other. The soil stratum is 10-meter thick with the pervious stratum on top and bottom. Determine the time required for 50% consolidation. Given my coefficient of consolidation K is given. Sorry, by coefficient of permeability K is given, AB is given, and the E is given. So here what I have to do is that from the coefficient of uh, uh, permeability, I have to find out the coefficient of consolidation CV. Okay, with the help of EV and E. Okay, after that I can find out the time factor, and then from the time factor I can find out the this one time factor I can find out the time required. Okay, so let us solve this. We have K as AVS CV is 8 W, right? So K, it's nothing but K into MV by gamma W. So MV is nothing but AV by 1 plus E. So I can get this. CV is like this. So 1 plus 2. So what is AV? 0 0.0003 10 to the power minus 3 centimeter per second. Okay. Now, top and determine the soil setup with pervious stratum on top and bottom. So again, you can see this is the clay. Again, this is rear drainage. Here, bottom is a double drainage condition. So HDR is nothing but 10 by 2. It is 5 meters. So now we calculate T50 is CBT50 by HDR square. So T50 I know 0.197. CV is 10 to the power minus 3. T50 by 5 square. So take care of the units and then if you calculate, you will get T. Just a second. I made some mistake here. No, it's fine. The previous one, I think I made some mistake. Yeah. Yeah. This one was 41.04 days. Yeah. Yeah. Now it's fine. 41.04 days, and this one will be 570 days. Yeah, same problem. So both the problems are almost similar. Okay, well, here there CV was directly given to you, and here you had to calculate the CV from your AV. That's all. That's all. Other everything is same. Okay, other everything is same. Now let us see this. A homogeneous clay layer 12 meter thick is expected to have an ultimate settlement of 322 mm. After a time span of 3 years, the average settlement was measured to be 152 mm. How much longer will it take for the average settlement to attain to 37 mm? Okay, the homogeneous clay layer 12 meter thick is expected to have an ultimate settlement of 322 mm. After a time span of 3 years, the average settlement was measured to be 152. Ultimate settlement is 322 mm. In 3 years, the settlement that occurs is 152 mm. So 152 by 322 will be my degree of settlement after 3 years, right? So 152 by 322 will be my degree of settlement after a span of 3 years. How much longer will it take for the average settlement to attain 237? That we need to find. So first, let us find U1. So U1 is the initial degree of settlement, right? So initial degree of settlement U1 is 152 by 322. That is 0.472. This is 47.2% settlement happens in 3 years. We need to find out 237. It is 0.736. 73.6% settlement happens in how many years? So this we need to find out. Again, for U1 less than 60%, we will be having, you can use U1 pi by 4 U1 square. So this will give us pi by 4 into 0.472 square, that is 0.175. Okay. Right, so we have that times 3. 3, so 3 years. 3 from here CVT square I will get this as, and 175 by 3. So next for this one we need a TV2. Now TV2 for more than 60% settlement we have this relation, right? 933 log 10 100 minus how much? 73.6. And I will get 0.455. So now I can write 0.455 is equal to CV by D square. I already know 0.0583 times T2. I can get T2 is equal to 7.8 years. So for 152 mm settlement, 3 years is taken, and for 237 mm settlement, 7.8 years. Okay, so this is how we need to solve it. Okay. Okay, I hope this is clear. If you have any doubt, you can ask me right now. Okay, very simple. First, you find a degree of settlement and you calculate the corresponding TV, and from TV, we get the time. Okay, that's the main basic concept. That's all, nothing else. All right, please let me know if you have any doubts. I hope this is clear. Huh? It's very straightforward and simple. Okay, if we can proceed to the next problem. It's also similar. This one also you can try by yourself once. At a given site having a clay layer 8 meter thick with single drainage, okay, remember the single drainage, a uniform fill that was constructed resulted in a settlement of 5 centimeters in 1 year, corresponding to 50% average degree of consolidation. So 5 centimeter settlement, which is nothing but 50% of the total settlement. It was found that a neighboring site, the same type of clay exists, but having a different thickness of 16 mm. Okay, 16 meter. So previously thickness was 8 meter, now thickness is 16 meter. How long will it take for 50% consolidation to occur, and what will be the magnitude of the settlement if for the magnitude of settlement if a field of the same magnitude as site A was to be constructed in the site B? Because the same soil, but the thickness of the clay layers are different. In that case, we have to calculate the time required. Okay, that's the question. Now let us see. Now let us first see for the A, A site, site A. Again, we have right. You can easily find CV from here. So TV I know for 50% is what? 0.197. T is the time. So in 1 year, so I put 1 year, and D is the single drainage. So directly we'll put the thickness as the drainage path, that is 8 to 8 square. From here I can get the CV. Okay. Okay. So how to take it? So I have H1 as 8 meter. I have delta H1 as 5 centimeter, and my U1 percent is 50%. Okay. Now let us see for side B. And so TV is same again, 50%, so 0.197. CV, since the soil is same, since the soil in both the fields are same, so I will use this. I can use the same CV, since CV is nothing but a soil property, right? Soil property. For the same type of soil, CV will be same. T2 by 16, 8, 16. Okay, okay, by 16 squares. Let T2 as 4 years. Okay, so if if the thickness of the soil layer is halved, sorry, the thickness of the soil layer is doubled, then the time required increases by 4 times. Okay, time required initially, see here it was 1 year, now the time required becomes 4 years. Okay, time required also increases. Now, how long we found out? Now, what will be the magnitude of settlement? We need to also find out the magnitude of the settlement. So we have delta H as MB delta sigma into H naught. So from here I can write delta 1 by H1 by H2, right? For because these are the same. Okay, so from here I can write 5 by delta H2 is 8 by 16. So I can get delta H2, yes, that's it. Okay, quite simple. So you can see settlement was 5 centimeter. The settlement also increased, doubled. With the doubling of the thickness of the clay layer, the time required quadrupled and the settlement doubled. Okay. Okay. Now let us see this problem. A settlement analysis carried out for a proposed structure indicates that 5 centimeter of settlement will occur in 5 years. Okay, so 5 centimeters of settlement will occur in 5 years and the final settlement will be 25. So 5 by 25 we can get the degree of settlement. 5 centimeter by 25 centimeter we can get the degree of settlement. That much degree of settlement is achieved in 5 years. So I can find out the degree from the degree of settlement. I can find out the TV from TV, the time factor. The time factor I know, the time I know, the thickness of the clear I know. I can find out the coefficient of consolidation. Okay. The computation was made on the basis of double drainage condition. However, subsequent borings establish only single drainage condition. Calculate the final settlement and the settlement in 5 years for the change condition. Okay. So initially the calculation was done for a double drainage condition. So but finally it was found that the condition is of double drainage, a single drainage. In that case, how much settlement will occur and occur in the same time frame, that we need to find out. So let us do. First we have 5 centimeter settlement happens in how much? 5 years. The final settlement is 25 centimeter. So what is U1 and what is my, so double drainage condition, thickness, uh, so if the thickness of the clear layer is say H, then we have drainage path as H by 2 for double drainage condition. So now if TV, right? So for 20% settlement, this is my TV. Now I can relate TV to CVT T square. Can find out 0.0314. Okay, this I got. Now for second case, T is again 5 years. PV is 5 by 4 square. Also is equal to CVT by D square. Now pi by 4 d square is equal to CV T by D square. Now the case is what? Single drainage. So directly I will have the thickness. It is H square. Okay. As I can write pi by 4 into U square is equal to 1.5. Okay, so CV by H square I replaced by 1.57 into 10 to the power minus 3 into 5. From here I can get U as U square as delta H2 will be nothing but 0.1 times 25 is 2. Okay, so this is my final. Okay, so if we consider double drainage condition, then the same time frame 5 centimeter of settlement happened. But if we consider single drainage condition, in the same time frame only 1 centimeter of settlement will happen. So 2.5 centimeter of settlement. This settlement is half. Okay. See this. A clay layer 8 meter thick is subjected to a pressure of 70 kPa. If the layer, uh, if the layer, if a double drainage, if the layer a double drainage and undergoes 50% consolidation in 1 year, determine the coefficient of consolidation. If the coefficient of permeability is 0.04 meter per year, determine the settlement in 1 year. The first thing that we need to do is that we need to determine the coefficient of consolidation CV. It's given the double drainage occurs and occurs 50% consolidation in 1 year. So time I know, TV I know, CV I can find out. And also the double drainage I know. So drainage path HDR I know. Okay. That I can find out. So CV I can find out. This is 0.197. CV I don't know. Time is 1 year. And D is H by 2, 8 by 2 square. Okay. From here I can get CV as 3.152 meters square per year. Okay, I got CV, right? Next is, if the coefficient of permeability is this much, determine the settlement in 1 year. Determine the settlement in 1 year. Now, CV is KMB. From here, I can get MVS K CV gamma W. So K is given 0.040. CV also I have 3.152 into 9.81. So from here I can get MVS 1.3 into 10 to the power minus 3 meter square plus pi kilonewton. Now delta H is what? MV H. So 0.78 meter. So this is the total settlement. Total 100% this much consolidation settlement will happen. 0.728. Now it is given in the under 50% consolidation. So for in 1 year we have 50% settlement or consolidation. Therefore, it is 0.728 times 0.5 is 0.36 meter settlement. Will happen in 1 year. Okay. For the given arrangement, find the settlement by dividing the clay layer in clay into 4 layers. So we have this, we have a footing, then below that we have a clay layer. So it is asked us by dividing the clay into 4 layers, we need to find out the settlement. Okay, there are 1, 2, 3, and 4. Now what we need to do, at the center of each layer, we need to calculate the effective stresses, right? Effective stresses, increasing stress, and then we need to find out the settlement. Okay, that's how we need to do. So how will we do that? Let us see. So we considered that this load is spread by the footing into the layers in the 2 by 1. 2 is 2 horizontal into is to 1 vertical fashion. Okay, in that way it's distributed. The load is distributed. Okay. Let's see how to. Okay, 1.5 plus 0.25. I am getting from here to it is 0.25. So 1.75 times how much? 20. It's given 20. It's 35. Now what is the increase? Increasing pressure, it's 225 by How much? 1.5 by 1.5, right? So it's 1.5 plus 2 times 2 into 0.2 is square. So this will come out as 36 kilonewton per meter square. Good settlement 1 is 2.07. It's given. Thickness of clay is 0.5. 0.8. 35 plus 36 by 35. What is 5.97? And if you come in meters, then you convert it to millimeters to come out as 5.97. Now, similarly, we'll do for layer 2. Five plus 55 plus how much? 0.5 into 20. Similarly, for layer 3, we'll get S3 as 0.78 mm. And layer 4, I'm not repeating, so directly giving you the settlement values. Layer 4, you will get 0.39 mm. So, total settlement around 9. Okay, this one you can do by yourself as an homework. You can do in detail by yourself, and you can check if you're getting the same values or not. All right. Yeah. See what's there next. Hmm. Second. Yeah. Yeah. So let us see this problem. A saturated soil 6 meter thick lies above an impervious stratum and below a pervious stratum. It has a compression index of 0.28 and a coefficient of permeability of 3 to the power minus 4 centimeter per second. Its void ratio at a stress of 150 kPa is 1.95. Determine this. Okay. We need to determine the change in void ratio due to an increase in stress to 210 kPa, settlement of the soil stratum due to the above increase in stress. Okay, so if the stress increases to 210 kPa, we need to find out the change in void ratio and then subsequent change in the settlement. Time required for 50% consolidation and the amount of settlement which will take place in 1 hour. The ultimate settlement of the stratum was 72 centimeter. Okay, we'll solve it step by step. Okay, nothing to worry. It's also a simple problem like the previous one. So yeah. So let us not take TVS 0.2, we'll take 0.197 itself. Okay. So also 6 meter thick layer is there, and so it's only single drainage, right? So saturated soil stratum lies above an impervious stratum. So this is impermeable and this is pervious. So only one way this drainage can happen. Okay, so single drainage is there. It has a compression index of 0.28 and a coefficient of permeability of this much. Its void ratio at a stress of this much. Okay, determine this. Okay. Okay. So first is change in void ratio due to an increase in stress to 200. The first let us find out CC. CC is what? Delta E by this is the slope, right? CC is nothing but a coefficient of curvature is nothing but a slope, right? Not curvature, coefficient of consolidation compression index, right? This is nothing but the compression index. The compression index is nothing but the slope of the void ratio versus log of the pressure plot, right? So log, from here we can get, okay. So initially the stress was 150, and then it reduced to 210. So so from there we can get the change in void ratio. Change in void ratio is 0.041. Well, this is the change in void ratio. Okay, so first thing we found out. Okay, first we are asked to find the change in void ratio. We calculated the change in void ratio. Next is settlement of the soil system to the above system. So same we will use the settlement relation. Six is the thickness. 1 plus E naught. So E naught is given. Initial void ratio at a stress of 150 is 1.95. Okay, this one will calculate this. Check how much you are getting. This much will be the settlement of the soil setup due to the increase in stress from 150 to 210. 83 point. Next, we have the time required for 50% consolidation. So we have dV 80 by t square. We need to find out CV first. Okay, CV. The coefficient of consolidation we need to find out. So what is AV? AV is delta E by delta sigma. Delta E is I know 0.041. Delta sigma also I know 210 minus 150 will come out as 6.83 into 10 to the power minus 4. Then I can find out the MV. Okay. Okay, so AV I got, MV I got. Now we can find out CV easily. A by gamma W into MV. So 3.5 into 10 to the power minus 4 by 9.8. Convert the units. It's 2 at 1.54 into 10 to the power minus 3 meters square per second. From now I will get dV. Time by d, that is the thickness, 6 meters. Single drainage, so directly we will get 6 square. Can get ds 1.279 hours. Okay, so I got the time is 1.279 hours. Time required for 50%. Next is the amount of settlement which will take place in 1 hour. So in 1 hour, what is the degree of settlement that I have to find out? So first I will find out TV. From TV I will find out U. From U I calculate the U is the degree of settlement, and that I will directly multiply with the ultimate settlement. I will give me the settlement in 1 hour. 1 hour. 1 hour, 3600 seconds divided by 6 square, 0.154. So this is less than 0.197. That is obviously a degree of consolidation is less than 50%. So I can use this. Pi by 4 into u square is equal to 0.157. From here, u will come out as 0.4428. Therefore, settlement in 1 hour is 0.4428 times the ultimate settlement. The ultimate settlement is how much? 72. So this will come out as 31.88 centimeter. So this much settlement happens in 1 hour. All right. Yeah. Okay. So next, so this is the last problem from for today. So let us see it. The coefficient of consolidation of a clay was found to be the CV. CV is found as 0.955 meter square per millimeter square per minute. The final consolidation settlement for a 5 meter thick layer of this clay was calculated as 280 mm. The final consolidation settlement for a 5 meter thick layer of this clay was calculated as 280 mm. So the coefficient of the consolidation is given. The final consolidation is also given as 280 mm for a 5 meter. Assuming a uniform initial excess pore water pressure distribution and permeable layer to be present both above and below the clay layer, compute the so permeable layer is present both above and below the clear. That means double drainage condition. Okay. And we have to assume uniform initial product. Everywhere we are assuming this only, that the initial excess water pressure is uniform across the soil layer. Compute the settlement time for 90% primary consolidation and settlement of 100 mm. So these two cases we need to calculate. Okay, these two cases we need to calculate. Number one, let us see. The CV, the coefficient of consolidation is given as 0.955. TV for U% L to 90% is 0.848. Okay, for 90, if you can use the relation, then if you put use it 90%, you will see that you will get TV for 90% consolidation as 0.848. Okay, this you can remember. For 90% is 0.848, for 50% is for that is 0.197. Okay, for 90% it's 0.848 time factor, and for 50% consolidation the time factor is 0.197. Now TV, this time is unknown, right? This time is unknown. Put all the values. This CV d square. So d is 5 meter thick. So 5 by 2 meters into 1000 mm square. So this one will come out as T is minutes, which is nothing but days. It's nothing but 10.56 years. That is for to achieve 90% of the primary consolidation. more than 10 years, 10 and a half years are required, almost 10.6 years are required. Okay, so a lot of time is required to achieve 90% settlement, primary consolidation settlement. Okay, for a soil of this nature, having a CV of this value, 0.955 mm square per minute, the soil, the time required to achieve 90% settlement is 10.56 years. Okay, now the next question is the time required for 100 settlement. Now, for that, first, what you have to do, you need to find out the your degree of settlement. Now, what is the final consolidation settlement? Final means 100% settlement is 280 mm. 100% settlement is 280 mm. So, if 100% settlement is 280 mm, then 100 mm will be how much? 100 by 280 is equal to 0.3571. That is 35.71%. Okay, now TV is pi by 4 into 0.3571 square. From here I can get TV as 0.10015. Now TV is CVT by T square. So CV I know 0.955 into T by D square. Again 2.5 into 1000 pi square. Okay. From here, I can get T is 0.10015 into 2.5 into 1000 square by 0.955. Can get TS 65541.3 minutes is nothing but 455 days, which is nothing but 1.25 years. So, to achieve 90% of the ultimate, this 90% of 280 mm, that much settlement, it requires 10.56 years. And to achieve 100% settlement, which is about 35% of the ultimate settlement, the time required is 1.25 years. So you can see the consolidation is a very slow process and it takes a lot of time. Okay, lot of time for the soil to consolidate and then settle. So if you want to accelerate the consolidation process, we need to use certain techniques such as using prefabricated vertical drains, sand drains, okay, um, then vacuum consolidation, all these things, uh, things we need to use. So these things are generally discussed in ground improvement techniques or geosynthetic geosynthetic and reinforced soil structures. Those courses, in those courses, these techniques are discussed in detail, and we will not discuss those. The sand drains part we will probably discuss in the previous next class if we have the scope. The sand drains you will see along with the radial, along with the vertical drainage, we also have the radial drainage. Okay, along with the vertical drainage, with the help of sand drains, we can also have some radial drainage in the soil. So due to that, what happens, the consolidation process accelerates a lot. Okay, accelerates a lot. Okay, with due to along with the vertical drainage, we also have the radial drainage with the help of sand drains. Okay, it helps us to reduce the time required for the consolidation settlement to happen. We can accelerate the consolidation settlement. Okay, so this was all for today's session. We solved a lot of problems, 12 problems, a lot. I suggest that you please solve these problems by yourselves again. Okay, just try to solve these problems yourselves again and again. Try to do it. Okay, and if you solve them properly, I hope that it will be sufficient for your exam purpose too. Okay, so I suggest you solve more and more problems yourself. Read the textbooks properly. Reading the textbooks is very much necessary. Okay, so please read the textbook, solve the problems, and eh, this will help you to grasp better hold of the concepts. Okay, as much more the problems you solve, the more better the concepts will get clear to you. We understand the concepts more much in a much better way. Okay, so with this we'll end today's session. We have 9 minutes left, so 8 minutes left for this session. So I'll be here. If you have any doubts, you can ask me, or if not, you can leave. So I'll be here for some more time till 8 o'clock. And till that time, if you have any doubts, please feel free to ask. Okay, else you are free to leave. We have solved a lot of problems in a short amount of time, and I hope that this you understood the problems how we solved this. Okay. So thank you for attending and see you on Friday. Okay, we will have the eighth week discussion session. We'll have the eighth week discussion session on Friday. Okay, don't forget Friday same time. This coming Friday, that is the 21st. Okay, this coming Friday we'll have the same discussion session from 6 p.m. to 8 p.m. So don't forget to attend it. Okay, we'll discuss some more problems like this. So we are just nearing the end of this course. Okay, 8, 9, 10, almost 12 weeks we have, right? 12 weeks of discussion. We'll be having 12 weeks of the course. 12-week course is a 12-week course, so 12-week discussions we'll have. So we have just finished the seventh. So 5 more weeks, and then after that 1 hour. In the 13th week, we will have just a 1 hour long discussion, the revision session or summary session. We will summarize all whatever we have studied in this 12th week. Okay, so yeah. Okay, so thank you for the. If you have any doubt, you can ask or you can leave.